Hey guys, in this video I want to discuss the specific tautomers of dicarbonyl compounds. So guys, I've already introduced the fact that tautomers happen to carbonyls whether you like it or not, okay? This is just a natural process that occurs at equilibrium. Now, just because it happens doesn't mean that it happens in very appreciable amounts, okay? In fact, most carbonyl compounds are going to favor the keto tautomer. Why? Thermodynamics, guys, it's just more stable. The keto tautomer is more stable than a vinyl alcohol, okay? But beta dicarbonyls are special, okay? Because beta dicarbonyls are shaped in such a way that they're actually going to favor the enol tautomer. How do we explain that? Let's look at the beta dicarbonyl for a second. First of all, let's define beta dicarbonyl, that you have one carbonyl and another one beta to the one that you currently have, okay? Now we remember that the alpha carbon of a carbonyl has a pKa of around 20, okay? So these are pKa's that we're talking about here. Does anyone want to take a stab at what the pKa is between a beta dicarbonyl? What's the pKa of this hydrogen here? Notice that now it has two carbonyls on both sides. Guys, this is going to be a ridiculous pKa of 10, okay? Depending, 9, 11, 13, around that area, okay? How do you explain that? That's a crazy acidity. That's like as acidic as ammonium. That's as acidic as NH4 positive with a positive charge. How do you get something that acidic that's just an alkane? Guys, because of the stability of the enol tautomer, okay? Look at what the enol tautomer is going to look like. The enol tautomer, first of all, you're going to have two tautomers that are possible. And what you're going to get, first of all, is a bunch of overlapping resonance atoms that can resonate. This is called conjugation. Conjugation makes molecules stable, right? Awesome. So conjugation is going to stabilize these guys. On top of that, we've even got hydrogen bonding, because the enol is going to be able to, the enol from one side is going to be able to hydrogen bond with the keto from the other. This is the enol side, and this is the keto side. It's going to be able to hydrogen bond with itself. So what winds up happening is that if you take away a proton from the beta dicarbonyl, the methylene carbon in the middle, you're actually going to get 75% enol at equilibrium, depending on what the R groups are, obviously. I mean, if these R groups are different things, the number will change a little bit. I'm just letting you know this is an extremely favored tautomerization. Okay? So beta dicarbonyl compounds are exceptionally acidic due to the high stability of the conjugate base. Okay? Now, one thing to keep in mind is that since this is going to happen so frequently, if you happen to have a chiral center at the alpha carbon, so let's say that this had been a chiral center. It's not now because I got two H's. But if it was a chiral center, that chiral center will always be racemized. Okay? What the heck does that mean? It just means that you can't isolate one enantiomer. You're going to wind up getting a mixture of both, 50-50. Why? Because when you form the enol, you're going to lose your stereochemistry. You're going to turn trigonoplanar. You're going to lose the wedge and dash structure. And then when you add, you could either add the proton from the front or from the back. So you're going to get a racemization of any alpha carbon. That's pretty much as a rule. You're going to racemize all of your alpha carbons, okay? Awesome, guys. So this being said, beta dicarbonyls are very important for organic synthesis because they're so good at doing tautomerization. So let's do this problem here. I want you guys to look at the problem and evaluate which of these beta dicarbonyls is going to be the most acidic one of all. Think about the one that can form the most tautomers, okay? So do that and then I'll answer.